Welcome to the International Solar Alliance Expert Training course. Today's session is about ensuring quality in off-grid rural electrification projects. My name is Jorge Ortiz González and I will be the lecturer today. This expert training series is supported by the International Solar Alliance, the Clean Energy Solutions Center and Carbon Trust. As a small introduction, I am a PV solar mini-grid engineer at Trama Tecnoambiental. Trama Tecnoambiental is an international consulting and engineering company specialized in distribution generation through renewable energies in rural contexts. It has been running since 1986, developing the first mini-grid project in Spain in the early 1990s, and later on applying its expertise in energy access projects all over the world. This training is part of Module 7 Off-Grid Solar and focuses on the issue of quality assurance in off-grid solar projects. Quality assurance may be defined as a system or process which assures a certain level of ongoing quality in a product. For the off-grid sector, several organizations have been working on quality-related topics, and we would like to mention here some of them. First of all, we have the numerous standards set by the International Electrotechnical Commission, or IEC. Within the IEC, Technical Committee number 82 is dealing with PV solar, and the Joint Working Group number 1 was set up specifically for off-grid PV systems, including decentralized rural electrification and hybrid systems. We also have the Lighting Global Program, which has also been instrumental in developing a quality assurance framework to serve the off-grid sector with test methods and certifications. They have focused on Pico PV and solar home system products. Pico PV products normally range up to 10 watts, whereas solar home systems can go up to 350 watts. Its quality assurance framework serves as the foundation of the IEC Technical Specification 62257-9-5, which applies to standalone renewable energy products, such as batteries and PV modules. As a third example, we have the collaboration between the National Renewable Energy Laboratory, or NREL, and Global Leap, which led to a quality assurance framework focused on mini-grids, including those mini-grids with renewable energy generation sources. Quality is a very broad topic, but during this session I will provide you with the most important tools to ensure the quality of an off-grid project. Such tools will be references to international standards, quality assurance frameworks, and also best practices based on past experiences from existing projects. We will cover the project phases starting from system design up to the operation and maintenance, passing through the component selection, logistics, installation, commissioning, and training. Let's start with the first phase, the system design. Sizing an off-grid PV system or mini-grid depends on a large amount of parameters, and finding an accurate solution requires the use of specialized software. These parameters are introduced to the software via inputs. Some examples can be the demand profile of the power needed at each time of the day, or the costs of the components and the fuel, or the renewable energy resource potential, which is in our case the solar irradiance. The software will surely give us an output solution with optimum values for the PV capacity, the battery storage, and the inverter power output, for example. However, this solution can be useless for our project if we do not have a clear optimization objective. Having a clear optimization objective is critical to avoid under or oversizing the power plants, resulting in mismatch between demand and generation and the possible failure of the project. The optimization objective is focused on one or more indicators. Here we have grouped some examples of indicators in three categories, namely economic, technical, and environmental. An economic optimization objective could be to minimize the levelized cost of electricity, or to minimize the capex, for example. A technical objective could be to maximize resilience if the plant is connected to a weak grid, for example, or to maximize the fraction of renewable energies in order to follow some national regulatory requirements. Choosing your optimization objective will depend on how the project is being financed, its tariffs and other regulations, the uncertainty in the demand assessment, and the location of the project. For example, if the capex is 100% financed and we are in a remote location with high diesel prices, we may opt for minimizing OPEX by selecting a slightly bigger storage system and 100% solar mini-grid without any genset backup. On the contrary, if the capex is a private investment and the diesel prices are low, then the optimization objective will be to minimize the levelized cost of electricity. Once we have selected our optimization objective and we have simulated the optimum system, the software will output values such as the PV capacity, the storage capacity, the inverter power rating, and the diesel generator power rating. We then need to assess what is the optimal electrical architecture for our system. Here we can divide the possibilities in three groups, depending on the position of the PV array with respect to the batteries. If the PV array and batteries meet in the DC bus, we call it a DC coupled system. If they meet in the AC bus, it is an AC coupled system. And we have also the option to have both a DC coupled and an AC coupled PV array together, which we will call a mixed DC-AC system. Note that different manufacturers can give a different name for this mixed system. Also note that some systems may not include a diesel generator, although it is generally recommended as a backup energy source for emergency cases. Now, the optimal electrical architecture will depend on different factors. One is the load profile, meaning the power demand as a function of the time of the day. If there is a high demand during sun hours, an AC coupled system is more efficient because the PV power will just undergo one conversion step in the grid following PV inverter before going to the loads. The DC coupled system, as you can see on the left, will have to convert power twice, one time at the charge controller and another at the grid forming inverter. On the other hand, if there is a high demand during the night, the excess PV power will just need one conversion step at the charge controller in order to charge the batteries during the day in a DC coupled system. Whereas in the AC coupled system will not require two conversion steps, one at the grid following inverter and another one at the grid forming inverter. If the charge controller in the DC coupled system has a high efficiency MPP tracking, then DC coupling will be a more efficient solution than AC coupling. Another factor to consider is the cost. A carefully sized mixed system will most likely give the highest efficiency, but it will be more expensive. And yet another factor is the reliability and robustness of the system. In some AC coupled systems, if after several cloudy days the batteries get too discharged, the grid-forming inverter may switch off in order to protect the batteries. And without the grid-following PV inverter will not be able to inject the PV power required to charge the batteries again. Adding a small DC coupled array which ensures the battery charging can solve this problem, and then again moving into a mixed coupling. After choosing an appropriate electrical architecture, we have to select each system component. Here we will go through the most important components, namely the PV modules, batteries, charge controllers, PV inverters, and battery inverters. Let's start with the PV modules. It is always critical to require international normative references to the manufacturers. In the case of PV modules, the IEC 1215 and 61730 are compulsory, and the requirement for the 61701 and 62716 depends if the modules are installed in a corrosive environment. We suggest to use crystalline silicon-based PV modules in rural environments, both poly and monocrystalline, because they are the most mature technology nowadays in terms of reliability and cost. Moreover, all the modules within the same string must be of the same brand, model and production lot, having the same electrical characteristics, such as maximum power, short circuit current, current at maximum power, open circuit voltage, and voltage at maximum power. Note also that the nominal power of a PV module always comes with a tolerance. Positive tolerances are preferred and often offered by the manufacturers, together with efficiencies above 15%. Regarding the batteries, the IEC 61427 is the most important norm. If lithium batteries are used, important normative references are the IEC 62619 or the UN 38.3, which is a standard that will be required when transporting lithium batteries. Some recommended best practices are to ensure a high charging and discharging efficiency and a high number of cycles. At least 1500 cycles up to a state of charge of 20% is recommended. Moreover, a minimum self-discharge below 4% per month. The ambient temperature must be critically assessed, and we must always prevent the batteries from receiving direct sunlight. More than 3 parallel series are not recommended, so as to ensure a good voltage balance. Lead acid and lithium-ion batteries are the two most popular technologies nowadays. Choosing one or another is a very project-specific exercise. Lead-acid batteries are an economical and very robust technology, with a long proven track record. They have a good performance at low and high temperatures. Therefore, they do not require a reliable air conditioning system, which can be an advantage in very remote areas. They also offer more mature recycling programs. However, lithium batteries are getting increasingly popular, thanks to several technical advantages, like a higher amount of cycles at a higher depth of discharge, a higher energy density, and also a higher efficiency. If we select lead-acid battery, then we might need to choose between flooded tubular plate batteries, or OPZS, or closed tubular plate batteries, or OPZV. Again, there is not a good or bad decision. but it is rather a very project-specific choice. Flooded batteries require regular maintenance. Therefore, their success depends on a good maintenance team and schedule, together with the local availability of distilled water. On the other hand, they are also cheaper than OPC ZV. Closed batteries require very little maintenance, but they are more expensive. Also, take into account the logistics, because they have different storage requirements. Open batteries can be transported with the acid in a separate container, for example. The area available can also have an impact in your decision. Closed batteries can be installed horizontally, optimizing the area by stacking one on top of each other. On the contrary, flat batteries can only be installed in a vertical position, and they occupy more space. If we opt for lithium batteries, there are also different types. Here we mention two of the most common: the nickel manganese cobalt, or NMC, and the iron phosphate, or LFP. NMC batteries offer high specific energy, but they suffer from thermal runaway and require extra safety measures. On the other hand, LFP batteries have a lower specific energy, but they are more stable against high temperatures, making them more tolerant against abuses. Moving on to the charge controllers, the most important normative references are the IEC 62109, 62509, and also the UL 1741. Here we list some suggested best practices. For big systems like in PV mini-grids, controllers with maximum power point tracking shall be used. Compared to pulse width modulated charge controllers, MPPT controllers accept PV strings at higher voltages, are more efficient, and can handle higher power values, even though they are more expensive. Here we show a typical charging profile with 3 stages. A proper charging is imperative to maximize the battery performance. Therefore, the controller must be able to adapt each charging state according to the battery technology. The controller should also offer temperature-dependent charging thresholds. As a final comment, the algorithm used for the calculation of the state of charge of the batteries should take into account the measured battery temperature. Regarding the PV inverters, the most important normative references are the IEC 62109 and 62477. The use of string inverters with maximum power point tracking is recommended. Nowadays, they are a mature and efficient technology, offering competitive prices. They have lower power outputs than central inverters, which means that we will need a higher number of inverters. However, this is indeed an advantage, especially in remote rural locations, because if one inverter breaks down, we might need to wait weeks until the new inverter arrives. Take into account the temperature derating curve to be aware of the loss of power output at higher temperatures. Ensure the compatibility with the battery inverter in terms of communication and control. Also, oversizing the PV array nominal capacity with respect to the nominal power output of the inverter is a common practice, but one should always use specialized software to simulate the energy lost when the inverter is clipping the PV output. This will not only depend on the ratio, but also on the location of the project and the PV array orientation and tilt. Finally, the ratio between the power of the PV inverter versus the power of the battery inverter must be within the manufacturer limit. In the example below, the loads shut down suddenly. The PV inverter is still producing power, which then has to flow towards the battery inverter. If this incoming power is above the battery inverter's limit, the stability of the grid can be compromised, or the system may even shut down in the worst case. Regarding battery inverters, the most important normative references are the IEC 62109 and also the IEC 61000. Their power output also decreases with increasing temperature. Therefore, we shall always ask to the manufacturer for the derating curve. Here we plot an example curve of an existing inverter. When specifying the power output, take into account its output power depending also on the overloading duration. It is common practice to specify the 30-minute power, for example. The inverter shall provide means of regulating its active power output, for example, depending on an external signal from the power management system. In some cases, it can also curtail the power of the PV inverters in an AC coupled system by raising the grid frequency when the batteries are charged and the PV generation is high compared to the loads. Moreover, it is critical that the manufacturer ensures a compatible communication bus with all other system components, such as PV inverter and controller. It is preferred to use inverters that allow a modular design which can easily expand the installed capacity in the future. As a final suggestion, if connected to the grid, keep in mind the grid reliability when setting the inverter's parameters. Here we show the minimum warranties that we would expect for each component. Please note that this depends strongly on the manufacturer, and some manufacturers offer longer warranties. PV modules normally offer 10 years of product warranty and 25 years of performance warranty. Charge controllers and PV inverters offer around 5 years, and battery inverters between 2 and 5 years. Regarding the batteries, it depends on the chemistry. Between 1 and 2 years for lead acid batteries and between 5 and 10 years for lithium batteries. Okay, let's move on to the next phase, logistics. A typical logistic process would involve the following steps. First, an inspection of goods and their respective certification by an independent party. Then, a container optimization to maximize the amount of materials that can be fit within the container. Also, paperwork such as transport insurances and shipping documents. Then, custom release. We would like to stress the importance of having a competent local agent with well-defined responsibilities in order to avoid costly delays at customs office. Last but not least, inland transport to the site. In off-grid projects at very remote locations, we must not underestimate the extra time and cost associated to the inland transport of materials. We can easily come across narrow dirt tracks, small boats, or blocked roads. Employing the local community is also a good practice in order to improve the local economy as well as their engagement and feeling of ownership. Moreover, ensure that lithium batteries are transported with a reliable air conditioning system that can endure unforeseen incidents like blocked roads. This is especially important when using NMC lithium batteries. Once the materials arrive to the project's location, the next phase is the installation of the power plant. As a general comment, it is recommended to consider added value solutions. A good example is the use of a pergola for mounting the PV modules. Depending on the project, a pergola would provide a shaded area that could be used for community engagement activities, for example. One could also install the technical room below the pergola in order to decrease its room temperature. This would benefit the batteries and other electrical equipment, improving their performance and increasing their lifespan. In remote off-grid projects at communities with limited technical skills, we must put special focus on the prevention of accidents. Regarding electrical safety, we must take into account that health effects start taking place when a current of several milliamperes crosses a human body. This current follows Ohm's law. Therefore, reducing the system voltage is an effective measure to reduce the electrical risks. The IEC defines the extra low voltage below 50 volts for alternating current and below 120 volts for direct current. The AC voltage of the power plant will typically depend on the local grid and/or the appliances used by the consumers. Even if there is a medium voltage line between the plant and the consumers, the plant will inevitably use an AC voltage above 50 volts. However, on the DC side, we have more freedom. We can design PV strings with a maximum of 3 PV modules connected in series in order to limit the DC voltage of the system below 120 volts. However, when dealing with high power systems, we might need to go for higher DC voltages to ensure acceptable resistive losses. Also, powerful battery inverters, which have DC inputs in the range of hundreds of volts, might be needed in microgrids with power outputs beyond 250 kilowatt. In such cases, enhanced safety measures shall be taken into account. Here we list some best practices to take into account during installation. Always follow national and international standards to ensure the safety of the personnel and the components. Some important international standards regarding PV systems are the IEC 603/64, the 615/57, and the 625/48. The IEC 624/85 is a good reference for the safety requirements during battery installation. Consider the local environmental effects on the components under installation, such as unusual high temperatures, corrosive environments, rainy seasons, or potential hurricanes. Also, if open lead-acid batteries are used, special measures shall be taken into account. These batteries emit hydrogen gas, which poses explosion hazards. The battery room must be then ventilated according to the requirements specified in the IEC 62485. Furthermore, measures to reduce the risk of electrostatic discharge must be taken, such as the use of cotton clothing. Always follow strictly the manufacturer recommendations. So, once the system is installed, the next phase is the commissioning of the system. This phase has three main objectives. First, to check the process to ensure that the system installation meets the requirements set forth in the implementation contract between the developer and the implementer. Second, to test the process to ensure that the system operates according to the functional part of the implementation contract. Third, once the parties come to an agreement, to transfer the responsibility of the system. Some relevant standards to follow are the IEC 62446-1, which sets the requirements for testing, documentation and maintenance of grid-connected PV systems, and the IEC 62257-6, which focuses on more general hybrid systems and mini-grids. The commissioning phase can be divided in the following steps. Before anything, the preparation step checks that all non-operational contractual requirements are met. This includes checking the documentation, the manuals, the spare parts, the drawings, procedures, etc. Then, an evaluation of the conformity of the installed system with the accepted design, to check that the equipment complies to the design. If some differences exist, they must be explained, documented, and agreed upon. After this, an evaluation of the qualification of the installation, to check that the system is ready to be operated. Next step will involve the preliminary tests, to check that the components operate correctly. Next comes the performance test, which will check all the operating performance parameters of the whole system. And finally, an agreement between the parties in order to transfer the responsibility of the system. Each step must have its associated commissioning report, signed by all relevant parties. When drafting a commissioning report, we suggest to follow code-compliant test descriptions and example reports that can be found in international standards such as the IEC 62446-1 and the 62257 series. Here we show an example of a PV array test report, which would be attached within the commissioning report of a PV system. The report specifies which parameters must be measured or recorded per each PV string. These include electrical parameters such as the array's open circuit voltage and short circuit current, specifications of components such as the overcurrent protection devices or the wirings, and also tests such as the polarity check or the array insulation resistance, among others. Next phase is the training phase. Chronologically speaking, it does not need to immediately follow the commissioning phase. It will mostly run in parallel with other phases. Community involvement and training is a critical step in order to ensure the long-term sustainability of the project, and it must take place actually from the very first steps of the project. The social structure and its traditions must be understood and respected in order not to leave any vulnerable group apart. Even before designing the system, it is important to assess the willingness to pay of the community and also a potential expansion of the demand once they get access to 24-hour reliable electricity. Engaging the community in the decision-making process is also important in order for the community to feel the ownership of the project and decrease the risk of future non-payments. For example, setting a local tariff committee would be an option to improve the community engagement. On the technical side, ensuring an operation and maintenance team with local participation is critical for the long-term project sustainability. We should note that O&M workers might leave the community in order to continue their working career somewhere else. Therefore, the training must be a continuous process that will give incentives to the people not to emigrate their communities and lose the local capacity. Training shall be also addressed to consumers. First of all, financial obligations have to be clearly defined from the very beginning, ideally via a written policy concerning the disconnection from the grid in case of non-payment. Safety is always critical, of course, especially in communities which did not have access to electricity before. But also energy efficiency. The message that an isolated mini-grid based on limited solar resource is not equivalent to the grid in the city shall be passed on. For example, the use of electricity for heating or cooking can be forbidden in some projects. This can be ensured by the use of smart meters, which limit the energy and power of a consumer. Finally, involving women in the process is highly recommended. We encourage you to visit the great work done by Barefoot College, Solar Sister, or Grameen Sakti. Demand-side management is an important topic in renewable energy-based projects. Demand-side management is defined as the modification of the consumer energy and or power demand through methods such as financial incentives, with the objective of matching the demand with the energy generation. Here we present a recap graph with an example. As you may have seen in other webinars, during the sun hours, when the batteries are fully charged, there is a bonus period with lower electricity tariffs. On the other hand, during the morning and the evening, where there is little or no PV generation, there is a restriction period with higher electricity prices. But how is demand-side management put into practice? Well, there are several ways. One way to do so is through real-time communication by detecting frequency changes in the grid. Some grid-forming battery inverters offer the possibility of programming the frequency depending on the battery voltage. Hereby we plot an example. F_num is the nominal frequency, for example 50 Hz, and delta F is the frequency variation allowed in our system. The black solid curve is the programmed frequency variation. In the x-axis, a higher battery voltage means a higher state of charge, hence more energy available in the system. As the batteries get charged, the inverter will progressively raise the frequency of the grid. Now, some smart meters can detect the grid frequency and adapt the price accordingly. To implement the demand-side management strategy, we could give, for example, an incentive when the frequency is above the nominal frequency plus delta F divided by 2. We would be in the green regime, called bonus. On the contrary, we could set a higher tariff when the frequency is lower than the nominal frequency minus delta F divided by 2. We would be in the red regime, called restriction. This would happen when the batteries have a low state of charge. In such a way, we could set the price depending on the energy available in the system. The last phase deals with the operation and maintenance of the system. The operation phase aims to manage and monitor the system and to respond to abnormal conditions via proper corrective actions. This guarantees the system's safety and allows to collect the data needed to perform a periodic analysis of the system's performance. The maintenance phase includes both preventive and corrective maintenance. It comprises periodic tests and inspections. As their name suggests, preventive maintenance prevents incidents, whereas corrective maintenance corrects them. The pictures below show a couple of examples. In the first one, the one on the left, the cable conduits were properly sealed in advance as a preventive action. In the second one, a corrective action must take place because the front glass of a PV module broke into pieces. It is recommended to spend a good amount of time and resources on preventive maintenance and to always include spare parts within the project's budget. Here we mention some references to be taken into account during the operation and maintenance phase. As always, it is recommended to follow national and international standards and protocols. In this case, the IEC 62257-6 contains maintenance and replacement recommendations for small renewable energy and hybrid systems. The IEC 62446-2 deals specifically with PV system maintenance, and the IEC 61724 with PV system performance monitoring and evaluation. The Quality Assurance Framework for Mini-grids, written by the National Renewable Energy Laboratories, can be of great help when characterizing the level of service that a mini-grid is providing. It categorizes the level of service into 3 groups: a base level, a standard level, and a high level. For each level of service, the framework quantifies parameters related to power quality and power reliability, as you can see in the table. Quality parameters can be maximum voltage imbalance between the phases, or frequency variations, or also number of allowed faults per day, for example. Reliability parameters are the indexes for system average interruption duration and for system average interruption frequency. We must also note that the IEC 62257-1 also provides a similar framework. Here we show some possible issues that can occur in a PV system. Do not leave vegetation unattended, otherwise you may end up with high shading losses, especially if the modules are mounted in a vertical position, as shown in the example. Shading losses as high as 30 or 40% have been observed in very arid environments. Therefore, plan ahead your cleaning maintenance with a clear protocol and responsibilities. The monitoring will depend on an irradiance sensor. This can be a pyranometer or a silicon-based cell, for example. Be sure that it is always clean and away from shading obstacles. Otherwise, the whole monitoring analysis can be useless. Cable defects are one of the most common incidents, and one of the most dangerous ones as well. Here we show a cut cable, which could have been better protected by avoiding the physical contact with sharp edges. Always use certified PV connectors of the same manufacturer and brand. A fault connection can be a source of energy loss, electrical arcs, and in the worst case, a fire event. Ensure that wild animals cannot enter inside junction boxes. They can cause dangerous short circuits and damage system components. We will now show an example of a maintenance schedule. There are 5 types of tasks, depending on how often they are performed. Constantly, every month, every quarter, every semester, and every year. We also characterize each task depending on the technical level required, from basic to professional. We will show first the tasks that must be performed constantly. Here we find general checks for the existence of operation and maintenance checklists, plans, logbooks, as-built plans of the power plant, technical documentation such as component datasheets, operation manuals, and the monitoring and evaluation plan and its latest reports. It is critical to always have these type of documents updated in physical format in the technical room of the power plant. The protocol also includes a basic check of the accessibility of the power plant, ensuring that only authorized personnel is allowed and that all signs are still in place. Now we will show the tasks that must be performed every month. Several tests are performed on the batteries. First, a general visual check, looking for possible sediments and crystals, measuring the electrolyte level, and assessing a possible corrosion and checking the connections. Also, we check the availability for the different instruments needed for maintenance, such as a hydrometer. Moreover, a battery voltage measurement is conducted. Then come the tests related to the data logging. The normal operator can check that the simple performance parameters agree with the system specifications and log them in the logbook. The supervisor is the one performing a more detailed check on the operational parameters, which are also logged. Lastly, there is a general check on the technical room. The operator checks the ventilation, the proper signing of the restricted areas, and the availability of the safety equipment such as fire extinguishers. We continue now with the tasks that must be performed every 4 months, or the quarterly tasks. These are mostly related with the PV generator and do not require advanced technical skills. Among the tasks, we can find cleaning the dirt away from the PV modules and a visual check for possible defects in the PV modules, such as hotspots or cracks. Also, the coating around the fixing points of the mounting structure is examined, as well as a visual check of all fixing screws, with special emphasis on their tightening and a possible corrosion. The operator also ensures a proper tightening, contact, and wiring of the radiation and temperature sensors. To finish with the PV generator, a visual check of all cables is performed. Regarding the batteries, the operator measures the density and voltage of each cell and fills them with distilled water. The only task that requires a supervisor is the downloading of all recorded data, together with a check on the raw data. Most of the tasks to be performed every 6 months require a professional electrician or a PV engineer. Concerning the PV generator, there is a prevention of possible plant growth, which could provoke unacceptable shading losses, and a complete check of the modules and their wiring. The battery cables and terminals are checked also, including the resistance to earth. The project supervisor performs a complete data analysis and prepares the evaluation reports to be presented to other stakeholders. Also, the inverter is checked, including its operation, screen, alarms, and modes. All the electric boxes are checked, both the DC and the AC boxes, including, among others, the condition of the cables and terminals, the overcurrent and overvoltage protection devices, the switches, and the earthing system. This example maintenance protocol includes 2 yearly tasks. One is a detailed professional check on the whole system, including all its elements and operational conditions. The second one is a visual check on how do the shades progress during the day, in order to ensure that there are no new shading obstacles that influence the PV output. This was just a quick example of a maintenance schedule. Remember that the maintenance manual must carefully explain step by step all the tasks and must be always present in the technical room. Also, the responsibilities must be clearly defined in the contract. Most importantly, remember that ensuring a constant operation and maintenance team made up of local personnel is critical for the long-term sustainability of the project. With this, I would like to close today's webinar on quality assurance in off-grid PV projects, where we have gone through each step of a project, from the system design until its operation and maintenance. I hope you enjoyed it, and I would like to thank you for your attention.